Hi, I'm Gary, and I want to show you how I use Cloudy. Okay, we've been talking about thermal equilibrium and how the cooling function is balanced by the mean photon energy. Today we're going to talk about how the spectrum changes when the cooling function or the abundances of the elements change. So we're going to change the metallicity over a very broad range and look at how the emission lines change. And the result would be surprising this spectrum does not change nearly as much as you think it should. This is the input script we're going to set up and run in the first instance. So this is going to be a constant temperature input script. So we're going to set a prefix of vary Z for varying metallicity, CT for constant temperature. So here are the metals. So metals is everything heavier than helium. Cloudy prefers log scales. So this is the abundance relative to solar. And so this would be about a half of solar is taken at face value. And it says vary, we're going to vary this. So this number is not used for anything. Rather, it's these grid points that are going to be used. So we're going to vary the metallicity from zero point 0.1 up to 10 times solar in quarter duct steps. Now, in this sim, we're going to do something on physical. We're going to hold the gas temperature constant at 10,000 degrees. So the temperature is the log of the temperature here. So we turned off the energy solver. So this is not going to conserve energy. It's not in thermal equilibrium. So now we're going to set up a sim to just get it to run. So we have a black body, a sumization parameter, a hydrogen density of 0, it's log, so it's 1 hydrogen per cubic centimeter. Stop zone 1 set DR, we've seen that a lot. Now we're going to save some output files. We save the grid points so that we can check the quality of the sims and then also get the parameters for the metallicity. Save overview has interesting information like the temperature. This is a new command, save abundances. So what this does is it saves the density of the first 30 elements. So the units are going to be log. It's going to be particles per cubic centimeter. So hydrogen atoms per cubic centimeter. For oxygen, it'll be oxygen atoms per cubic centimeter. And finally, we're going to say the intensity of the lines tabulated in this line list file. And that's a local file. So the way save line list works is it goes through this file, picks out all the lines, and then writes them into the intensities into this file here. So the final name of the file would be varyCCT.lin. So let's look at what's in the line list file. We just saved line list, not save lines. It's absolute, not ratio. So what it's going to do is look up these 4 lines and report the intensity relative to H beta. And it'll make some plots of that kind of thing. So we ran it, and this is the grid file for this case. So this shows it all false, no failures or warnings, exit codes are okay. And the last column here gives the grid point. So this is 10 minus 2 is solar up to 10 times solar. That looks okay. Let's look at the abundance file now. We've not seen that before. So this is seen in a spreadsheet. So this is increasing metallicity going down because every step produced one zone with one line. That's why this works so simply. So every line here is the next metallicity. The metallicities are listed in the grid file, not here. So we see hydrogen has a constant density, has a log, so it's 1 per cubic centimeter. Helium is constant at 0.1 per cubic centimeter. Now let's look at oxygen. So oxygen begins at this density per cubic centimeter and goes up, up, up. And by the end of the day here, it's at exactly 3 ducts higher than it was here. So this is 3. So the oxygen abundance has changed by 3 orders of magnitude. This plots the same thing. It just plots oxygen to hydrogen as a function of metallicity. Nothing to see here. It's a linear one-to-one correlation. Now let's look at the saved line list file. So again, this is for each metallicity in that grid. And what we see here might be what our common sense would tell us. This is the lowest metallicity, 1% of solar going up to 10 times solar with constant temperature. And you can see that line went up from 0.1 to 100, so it went up 3 decks also. So there's a one-to-one correlation between 507 and the oxygen abundance. If only life were that simple. And this is the O3 H beta ratio. So this is the predicted 507 to H beta ratio. And for solar, you would expect it's kind of high for an H2 region. For solar, it would be something like 7 or 8 for this ratio. And then if you look at a BPT diagram and look at this ratio for a large population of objects, the range is sort of somewhere around here, and that would tell you that there's not much of a range of metallicity. Now we're going to turn on the temperature solver. We're going to use thermal equilibrium, so we're going to conserve energy. So we remove the CT from the prefix name. Everything else is the same, except it did not include the constant temperature command. So everything else is the same. And let's run it, and let's look at 5007 to H beta. Well, what's going on here? The 5007 to H beta ratio ranges from 6.6.7, something like that, to a high of 3, and then back down to where it started when the metallicity varies by 2.5 decs. So vary the metallicity 2.5 decs, and this 507H beta ratio ranges over about a factor of 2, and it's not monotonic. And so it's what's going on? What's going on here? What's happening is clear once you look at the temperature file. So this is the gas kinetic temperature, the electron temperature, which is saved in the overview file. So we can see at 1% of solar, the temperature is up at 20,000 degrees. That's very hot for an H2 region. Down around the solar-ish, you have temperatures of 7 or 8,000 degrees. That's pretty typical for H2 regions in this part of the galaxy. If you keep increasing the metallicity, say 3 or 4 or 5 times solar, the gas temperature is down to room temperature. So the gas kinetic temperature falls inversely with the metallicity increasing, kinetic temperature goes down. This is the thermostat effect. So increasing the metallicity, what's happening here? Increasing the metallicity increases the cooling function, because that's just the sum of all the lines that are cooling. We know that heating equals cooling, so the heating term was this. We didn't change the star, so this is the same. This isn't a fast function of temperature. So we changed the cooling function, we changed how much metals there were. So how can the gas respond to keep this? Can't change the star. So the cycle that happens is you increase the metallicity, there's more oxygen, there's more cooling. So now cooling is bigger than heating as you do that. So the gas cools to decrease the cooling to match the heating. So the total cooling does not change. The total cooling is set by the mean photon energy times the recombination coefficient, because that's the total heating. So the total cooling doesn't change, but it's mostly forbidden lines, but which forbidden lines shifts around. So very high metallicity, the cooling is shifted into the infrared, and the fine structure lines are doing all the cooling. So thermal equilibrium acts as a thermostat to conserve energy. So the line spectrum itself doesn't change a lot because of energy balance, but which lines does change. So we'll talk next and look at some spectra of these various models in the next video. See you then.